The 18 electron rule can be used as a guide to showing the stability of inorganic and organometallic complexes. The number 18 comes about from the number of electrons associated with the inert gas configuration once we start including transition metals. So there's 2s electrons, 10d electrons and 6p making the 18. The method of counting is best shown using various examples. And the first one that we will do is manganese pentacarbonyl bromide. Now, the first ligand to consider, the carbonyl ligand or carbon monoxide, is a 2 electron donor. It almost always is 2 electrons, but sometimes 1 electron goes to each of 2 metals, but in most cases both electrons are going to the same metal. The remaining MnBr is can be considered in 2 ways. One, simply as Mn and Br in their neutral state, or we can consider them in the ionic form where we have Mn plus and Br minus. And this gives rise to 2 different ways of calculating the 18 electrons. Both are perfectly fine to use and both should give the same result. It is important though to remember not to switch systems while you're doing the counting so that you mix them up. Now if we look at the electronic configuration for manganese, we'll have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and then 3d5. And these electrons are in the inner shell, and we'll call these the core electrons, and these ones are in the outer shells, and we will determine them as valence electrons. Now you know that the s electrons tend to ionize first before the d's, and really we're looking at a d7 problem here. That's how we will count the manganese. So let's start doing our count. We have CO of 2 electrons and we've got 5 of them, and so that equals 10 electrons. The manganese is D7, and now we'll look at the bromine. And you'll recall from Lewis dot structure discussions that the halogens are just one short of the inert gas, and typically they will have 3 lone pairs and a single electron, and that electron is usually the electron that's formed in bonding, such as in the HBr bond. That's the electron that would participate there. So the bromo ligand in this case is going to be 1 electron. Total 18 electrons. If you want to look at it from the charged version of this, again we have CO 2 electrons times 5 equals 10. The manganese is now manganese 1 plus, and therefore that's lost an electron, it's now 6. But the bromine has now become bromide, gained an electron, and now becomes 2, and so the total of course is still 18 electrons. The next example that I'd like to look at is this guy, the cobalt pentamino chloro dichloride species. Now the stuff in the square brackets is the inner sphere coordination, which is what the 18 electrons is referring to. The stuff outside is outer sphere, and don't need to worry about that so much. So in fact what we could represent the whole thing by is something like that. Now cobalt has an electronic configuration of the same core as before, sorry, square brackets, and then for S2 and 3D7, which is going to give us D9 situation. Using the neutral method then, we would have cobalt with 9 electrons. Chlorine is the chloro ligand, which is that one there, has 1 electron. The ammonia, you'll recall that Lewis dot structure again would have had this kind of representation for ammonia, and so you end up with a lone pair of electrons. Those electrons can readily donate to the cobalt to become 2 electron donors. So again, we have 2 electrons, we have 5 of them, therefore 10 electrons. Now, you'll recall that we have this 2 plus charge here, and so the 2 plus requires that we actually take 2 electrons off the total. 9, 10, 20 minus 2 gives us the 18 electrons. If we do this same count by the charge method, first of all you have to look for the oxidation state of the cobalt. Well, we already have it as 2 plus, but then there's another third one in here as a result of that chloro ligand, so it's actually cobalt 3 plus here, and cobalt 3 plus would be D9 minus those 3 electrons, becoming a 6 electron problem. The ammonia, as before, will be 2 electrons times 5 equals 10, and our chloro has now become a chloride, and so that becomes a 2 electron. And add those up, and there's the 18 electrons. The next example is looking at a dimer. And the dimer is CP iron dicarbonyl dimer. Now let's explain what the CP is first of all. CP is C5H5. It's a 5 carbon ring. And each carbon has a hydrogen on it. So you can see that it's going to be unsaturated, and in fact it counts as a 5 electron donor, and there's delocalization going on in the middle. This dimer will have the structure of CP iron 1 carbonyl, and then we've got 2 carbonyls that are actually bridging between the iron and then the image, same image on the other side, and the whole thing is joined together with an iron-iron bond. Electronic configuration for iron, same core, and then it's 4s2, 3d6, or D8 species. So let's start doing the count. We have CP is 5 electrons. We have CO, which is 2 electrons for the terminal, and each of the bridging COs contributes 1 electron to each metal. So we have 2 of those. Around 1 ion. We're only looking around the 1 ion at the moment. That 1 ion is the 8 electrons that we've determined from D8. The other ion is contributing 1 electron, because you can see that there is an iron-iron bond that is included in the structure. And determining the electron count can help you decide whether one should have the formalism of a metal-metal bond or not. 5 plus 2 is 7, plus 2 more is 9, 17, 18 electrons. If we repeat that for, of course, doing it for the other ion will give you, of course, exactly the same result. If we look at the ionic method, then the ionic method would have it as ion 1 plus and Cp minus, in which case the Cp minus is a 6 electron donor. The COs are still 2 electrons. The bridging COs are 1 electrons times 2. The ion is now a 7 electron donor, and the other ion still remains as the 1. And so 8, 10, 17, 18. The last example that I want to look at in this case is this species. This is cobalt chloride that you buy. It's cobalt 2 chloride. Put it into water and you get the characteristic pink cobalt hexaco ion. Cobalt, same core as before. Just notice that the square brackets have different representations here. Perhaps a little confusing, but they're never used in the same situation to confuse them completely. The cobalt is 4s2 3d7, so again a D9 problem. So adding them up, 9 electrons for the cobalt. For the water, each water has a 2 electron donor. Remember, oxygen has lone pairs of electrons around it from its Lewis dot structure, and one of those pairs can donate towards the metal center, and we've got 6 of them. And then we have, in this case, we have outside the brackets the outer sphere chlorides. So again we had a 2 plus, because we could have written this as +2 like that. So treating it in that sense, because we've added a 2 plus, we have to take 2 electrons from our total, electrons being 9 minus, and so we've got 9 plus 12 is 21, minus 2 makes 19 electrons. Well. Doing it the charge way, we can see that the cobalt is actually cobalt 2 plus. And so that means that that's 7 electrons. The water is 2 electrons times 6, so that's still giving us 12 electrons. And we don't have to worry about any chlorides or anything. We also don't have to worry about the 2 plus charge, because that's already been taken care of by looking at the oxidation state of the cobalt. And so again we show that it's 19 electrons. An odd number of electrons means that we are talking about a paramagnetic species. That means that it's got an unpaired electron and will respond to a magnetic field. And of course, therefore, paramagnetic compounds do not conform to the 18 electron rule. So this video concludes here, just to give you, having given you a quick idea of how to count the 18 electron rule. It's not a hard and fast rule, but the method of counting is important, and you will encounter it in lots of different examples.